Okay, so we're going to talk about initial value problems for differential equations. We're going to start off with something very simple, which is first order system of differential equations. Okay? This is typically covered within the first week or two of beginning differential equations course. What differential equations tell you is something simple, a relationship between how a quantity is changing in time, versus itself in some nonlinear fashion often. Okay? So y could be, I don't know, airspeed. How does it change as a function of, of time and the current airspeed and so forth in some nonlinear fashion. So this is just a basic relationship. And the beauty of what calculus has done for us is it allowed us to develop a language in which to express most physical systems, right? Because everything's changing in time, and all we really want to do is know how that thing is changing. And if we can do it very well, then we can predict how either systems work, how the atmosphere moves, things like that, okay? So this is a simple one, first order differential equation, and typically we have to specify an initial condition. So for instance, at time 0, the state of the system is in this state right here. And if it's in that state, then it evolves according to this, and then you see what happens from there. Okay? Now, the idea behind calculus was to say, how do I define something as a continuous rate of change? Okay, so you spend a lot of time in calculus talking about the definition of a derivative. What does that mean? It's a limiting process as you take differences and they go to infinitely small. That doesn't work on a computer. Infinitesimal and infinity are not calculable on a computer. Okay? What the computer needs is something finite. And as long as it has something finite, it can do a lot of things very quickly with it. Okay? So instead of doing calculus, we're going to basically undo the calculus we learned. We're going to go back a step and talk about what did this mean in the first place. What is the derivative? Well, the derivative, if you remember, was defined as a limiting process. So if you took some difference, delta t going to 0, something like that, right? This was just the limit. This is the definition of the derivative in the first place, right? So this is freshman calculus. Now, so the idea was, once you got this process working, you said, okay, I can, now that I have the idea of a derivative in mind, I can start working with this stuff here, and I can use integration, differentiation, I can do differential equations, solving with analytic methods, and you move up to PDEs, and everything's based on this. But now when we go back to computation, we have to come back to this here. Because in the end, what we can say then is if this was the definition, and the idea is delta t gets very small, goes to 0, this is exactly the derivative. What we're going to do is now approximate this by saying, well, this then is nothing more than dy dt, something like this. Now this is a slope, rise over run. So this is your delta y over delta t, going from time t of n to time t of n plus 1, where t of n plus 1 is in the future, is approximately equal to this f now. It's not equal to it, right? This is the approximation. This derivative is actually this limit. But now what we're going to say is, well, how about if we go back a step and use this not as the limit delta t goes to 0, but just as delta t is small. The best we can do. So now you have a difference in y over a difference in t is now approximately equal to this thing here. And we're evaluating this right-hand side at t of n and y of n. We could have evaluated it at t of n plus 1, y of n plus 1. But we're choosing to evaluate it at a point we actually know. The idea is what we want to know is the future, and we have a present time of the system. So if you rearrange this, it comes up with a very simple scheme. So this thing here, if you just rearrange, you get this. This is called the Euler formula, or this is the Euler method for solving a differential equation. What it is, it just tells you that y of n plus 1, which is the solution in the future, delta t into the future, is equal to what it is now plus delta t times this. Now, delta t is typically small. So this is just a small correction to this, which gives me my future time. And this is nothing more than an iteration process, right? I have my solution now, and to get it into the future, I just take what I have now, I get a future point. Now I take that future point, plug it in here to get a further point into the future. So if I have the time at time 0, I can get then my solution at time delta t. If I have the solution at time delta t, I can get it at 2 delta t. 2 delta t gives me 3 delta t, and so forth. Now, one thing a computer is very good about is doing this kind of mindless mathematics. You put this in a for loop, have it iterate, boom, you crank out the solution very quickly. Okay? And it is typical that this is the kind of thing you want to set up in the computer. Most of the numerical solution techniques we're going to develop are going to be things as basic as that. How do I take some abstract mathematical idea and make it into what the computer can just iterate through very quickly? Because that's all the computer can really do. Add, subtract, multiply, divide very quickly. And you have to keep in mind that's all it can do. So you have to do all the brain work. This is just your lackey. Okay? So in general, methods of this form can be written like this. If I want to get my solution in the future, typically, this is the kind of algorithm you're trying to generate, which is my solution in the future is just some function of the current solution. And in particular, in this case, this f is equal to this thing here, but this is the more abstract idea. Take the solution now, get it into the future, and then you can just run this through an iteration loop and solve it as far as time as you want. Now, there's some issues we're going to have to consider with this. Is this thing stable? There's a lot of iteration processes that if you stick this in here, things go to infinity. You don't want that to happen. Have you ever seen anything go to infinity? I never have. But a computer will give you NaN, which means pretty much infinity. And that means that something went bad or wrong. Okay. Now, the Euler method here is sort of a general case of this, but really, in the end, what we're going to consider here at first is what are going to be called Runge-Kutta schemes. And Runge-Kutta schemes spelled, you might want to be tempted to say Runge-Kutta, but it's Runge-Kutta, okay? And is generally of this form. Your solution now, plus a little bit, gives you the future solution. It's as simple as that, on some ground level concept. Okay? The question is, I can control this right here. This phi. For this case, it was just this here. For the Euler method, this is what the phi was. But people are pretty clever. And they say, hey, I can cook up some better phis that give me much better accuracy. Okay? There's two things you're after when you do computations. Accuracy and speed. Don't underestimate the power of needing to be fast on a computer. If you work at Boeing and you've got to do simulation, three-dimensional simulation of airflow over a wing, okay? And you can tell the guy, hey, I got a really accurate code. It's going to take about 2 years to run. Versus, I got this one that can run for 2 weeks and get you an answer. That's going to be the better option for you, okay? That's very important, but you still need it to be accurate. So there's always this trade-off between trying to be fast, trying to be accurate. When we do just little simple baby problems, speed is not an issue. You throw it on any generic PC nowadays, you push return, you wait a second, out pops an answer. You don't really care if it took 1 second or 1.3 seconds or 2 seconds, right? That's not a big deal. When you start building serious codes, you do care about if it takes a day or a week, okay? So in some sense, this is aimed towards thinking about serious codes in that sense. All right, so what we want to talk about is this Runge-Kutta and try to figure out, let's talk about this thing right here. In particular, if we go back to this Euler method, I'm going to draw you a sketch of what we actually did. Here is time as it marches forward, and here is our solution y. And suppose this is like the exact solution. This is what it's supposed to be. This is actually what y of t is supposed to do. And we started here. I suppose that's my initial condition. That's my y of n. Now, what we did essentially with this Euler method is say, okay, how do I approximate the solution in the future? What we really did is we said, okay, what I want to do is we used basically a slope formula, rise over run. And what the slope did is it said, okay, to get to my next point, let's take the slope there, the tangent at that point, follow that tangent all the way till we get to the next time slot, which is Tn plus 1. And that is my predicted solution. You can see you'd make an error here, because you don't follow this exactly. But as delta t gets smaller, right, you're closer and closer to this curve. It takes you a little bit longer time to get off this curve. So this is kind of an exaggeration. You don't want ever this much error, okay, unless this is like a scale of 10 to the minus 6. Okay? But for the most part, this is kind of the idea. And then from here, you say, okay, I've already made a mistake, but that's all right. From here, I'm going to use the slope at this point, whatever the slope is here, and that's what's going to shoot me off to the next point. And then I'm going to use the slope here to get me to the next solution point. You see, you actually get an increase in error, and we're going to talk all about error next lecture. But for right now, we're just talking about schemes, and then we'll talk about what the related error is. Okay, so this is the kind of idea of what you can do. Now, one question you can really see, or that begs to be asked here is, this is a very simple idea, and it's in many ways, if you were left in a room all to yourself and locked it until you came up with a scheme that would work, this is probably what a lot of people would come up with. Hey, why don't I just approximate this by using the slope formula? Another thing you could do, though, is you could say, well, if I'm using the slope here to get over here, that's okay, but it's kind of one-sided. It's weighting all the accuracy on what the slope is over here. What if I used also the slope here and there? In other words, I weighted my next slope by using part of the slope here, part of the slope here. I could even use slope in the middle, so that essentially what I can get is an idea of how quickly this is changing, in which direction it's going. And if I use a little slope there, a little slope there, a little slope there, and I made, instead of, when I come back to this here, so in this piece here, this phi, instead of just using the slope at the left, why not use the slope at the left, a little bit of a slope on the right, a little slope in the middle, because this is telling me how things are changing. And if I use all these pieces of slope, I actually might be able to get a better prediction of what the future is going to look like. Okay? And that is exactly what you can do. And let me show you how you do this. And this is going to give you a clue of how some of these Runge-Kutta methods work, how you can generalize them. And then I'm not going to go into detail about working them out. Okay? Typically, these are the kind of things you might want to work out once in your lifetime. That's it. It doesn't have to be this year. Some other year when you're like just hanging out. Got less to do. Like maybe when you have kids, they're down for a nap. Get out. Yeah. Suggestion, take a nap when they take a nap, or else you're going to die. I didn't do that when my first was born, and I just spent 6 months walking around, bobbing my head. Okay, here we go. I'm done with that page. All right. So here, then, is the generalization. And this is where small boards are going to kill me. We'll see how I do with this. So my solution in the future, delta t into the future, is what it is now, the solution now at the current time t, plus delta t times, I'm going to generalize this. First, I'm going to put a weighting here. So this is like the Euler term. If I picked a to be 1, and that's it in here, then this is just the Euler, what Euler had given me before. My solution is what it is now, plus delta t times a times f. But now I have a in there. A is going to tell me the weight. How much weight am I placing on what the derivative is at the left point? But in addition to that, I'm going to place a little bit of weight somewhere else. B is going to be the weight. And my placement of this is some future time determined by P So that far into the future, where p is usually between 0 and 1, okay? So that will tell me if I go between 0 and 1, it's from the left to the right. And at okay. Future weight here too. So this is how far in the future. This is a little bit of weighting towards what the solution is. So I have 4 constants here: A, B, P, Q. Okay, they're generic. This tells me the weighting of the 2. This tells me the position of one relative to the other. So I have 4 parameters here I can play with. And the idea of what you want to do with these 4 parameters is, the basic idea is to try to come up with a scheme that allows you to take this step into the future and get better accuracy. And we're going to talk all about accuracy tomorrow, or sorry, Wednesday's lecture. But that's going to be the underlying principle here. So people spend a lot of time working on this stuff. If you get a better scheme, you can get better accuracy. And all that's based on Taylor expansions. Now, I'm not going to go into the details of the calculations, some of them in the notes. But I want to say this. Y of t plus delta t, if you use Taylor expansion on that, you get the following. It's y of t plus delta t f t y plus 1/2 delta t squared f of t t y of t plus 1/2 delta t squared f of y t y of t times f of t y of t plus, so this is just a plain expansion of this using Taylor's theorem, nothing else. Okay? So hopefully you learned that like second, third quarter calculus or something like this. Turns out the Taylor theory, their Taylor expansions are going to be one of the bases for doing almost everything computationally. I mean, it's amazing. Very simple ideas are going to be fundamental in applying here. But really, they're not big concepts. They're just applied sort of in new, elegant ways. Okay? So this is just a Taylor expansion of this, and you have 2-variable problem. And notice I've truncated it at terms that have order delta t cubed in front. Now, the idea is if delta t is small, that delta t squared terms are going to be bigger than delta t cubed terms. So you can kind of like disregard them. That's your error. Okay? So as long as delta t is small, you can think of this is my biggest term, this is my next biggest term, third biggest term, and so forth. Now notice a couple things. These have to match up. And what I can do is I can Taylor expand this part as well, but notice I already have this and this, this and this, delta t and this, and I can Taylor expand this and then just match up terms. This has to equal this. Now, when you do that, you get, let me pull it back over here, you get the following relationships. Three equations, 4 unknowns. That means it gives you it has 1 degree of freedom then. Okay? So there's infinite number of choices you can make here. Okay? Some of the more famous ones are pick A to be 1/2 or A to be 0. So if you pick A to be 1/2, then you can solve for the other 3 equations. What that's going to give you is what's called Juan's method. And if you pick A to be 0, you get second order Runge-Kutta. And these are just 2 standard techniques that oftentimes, if you see it in the literature, someone says, I'm using second order Runge-Kutta, that's what they mean. And these 2 are sort of like the most commonly used second order methods available. Okay? And it's all based on this idea. If you just Taylor expand both of these things, you're weighting the derivative. You're using part of the derivative of the left part and of the right part. So if you go back to this picture, what you're really doing in this is you're saying, instead of just shooting off from here, if I use the derivative here, suppose I just use half the derivative there, half the derivative there. So I'm really splitting the difference between these 2. Then that's how it would come across. And you think about it, I get a lot closer. That's the graphical interpretation. And if I do it in a very clever and smart way, what I'm really doing is picking out the derivative so I get really close to hitting that point exactly. Okay? Or getting closer and closer and closer. And that's what these methods do. Okay. Now, with that in mind, let me give you probably the most famous of them all. How many times have you seen that this year? Had that line in it, most famous of them all. Okay, nobody got that one? Yeah, and Rudolph, nobody sang it? Not once? You guys are shy still. That's okay, I'll warm you up. Fourth order. Now, if you've heard about me in my teaching, you know that the jokes are bad, but I try hard. So there's, I get credit points, extra effort, and that helps make up for things. Fourth order Runge-Kutta. This is probably the most standard used technique that you'll see. Okay? And let me just tell you what it does. My solution in the future is what it was, plus fourth order Runge-Kutta is a four-step process. Your solution in the future is what it is now, plus your time step, delta t, divided by 6, plus these four quantities you have to evaluate, where F1 is just the solution evaluated right now. That's your Euler term, essentially. F2 improves upon this by evaluating the solution halfway over to the next time step. So now it's evaluated not at t of n, but t of n plus delta t over 2. So in other words, halfway over to where you want to be. That's what you get, your F2. And you're using a correction from F1. F3 also evaluates halfway over. But now, same kind of idea. Now you're using an improved prediction because in theory, F1 gives you one correction, and then you're using that correction to get an even better correction, and that's going to give you even a better correction. And then finally use F4, which is equal to evaluate this all the way, the slope all the way at the right-hand side. And once you do this four-step process, you plug them in here. There's your solution, the delta t into the future. The beauty of this is that it gives you an error, global error, which is called delta t to the fourth. Okay, we'll talk about, and that's why it's called fourth order. The fourth order refers to the order of the error. So if you take a time step of 0.01, so it's 10 to the minus 2, your error you can expect to be on the level of 10 to the minus 2 raised to the fourth power, 10 to the minus 8. So that's where your error should be. So that's your accuracy you're starting to get out of this thing. Okay, very small, and you want it to be that way. Okay, second order accurate stuff, which is the second order stuff over here for this Runge-Kutta I talked about down here. If you take the same time step of 0.01, take negative 2, your accuracy is only that squared, so it gives you 10 to the minus 4. So you're a lot less accurate. Okay, so there's a big advantage to using something like this fourth order Runge-Kutta. But it does cost you. You can see that here. I mean, this is a four-step process that you have to build in an iteration scheme, right? So you're going to iterate this thing, and within each iteration, you've got to perform 4 calculations. That's costing you time. But it's buying you a lot of accuracy. Versus here, just iterate that directly. It's not costing you any time, but accuracy here is horrible. And often this scheme is also unstable in addition. So, don't be deceived by the simple path. Grasshopper. Okay. All right. Okay, so those are Runge-Kutta methods. And you see what we just started with is simple, basic idea. Definition of derivative, Taylor expansions. That's it. Right? Nothing fancier than that. But from those two simple concepts, you can build up into a fairly sophisticated idea of how to solve these problems already at this stage. And this fourth order Runge-Kutta is already sort of get you to the point where that's what people are using. It's not like, okay, here's a toy thing you'd never use. This is, you'd use that. Okay? Now, it would be unfair to start off with the definition of derivative and not talk about like the definition of the integral. Okay, because we have to have those two together, right? So now we go to a different type of numerical scheme for solving differential equations based upon just the idea of what's a derivative. Okay, these are called often, trick is to get it off without getting yourself all black. There we go. What are called Adams methods. Okay. Now, Adams methods are what's called oftentimes multi-stepping schemes, and I'll show you why in just a moment. But what they do is start off from a different premise, and you start off here, dy dt is equal to, there's our differential equation again. Now, the first approach we had to this was to say, well, dy dt, that's just a slope. That's just rise over run. It's delta y over delta t. And what we did is, by using that discrete slope, we wrote down this Euler formula from that. And we can generalize it up to something like a Runge-Kutta method. Adams methods do it a little differently. They say, integrate this thing. From t of n to t of n plus 1. And what do you get? Well, if you integrate this side, differentiation and integration undo each other, and you end up with y of n plus 1 minus y of n, if after you evaluate this thing at the limits, is equal to the integral of the right-hand side. Nothing so hard about that. And this is exact. So you can think about it this way. I can now move this y of n over, and look what I have again. I have an iteration scheme. Not quite yet, but I have something starting to look similar to what I had before. My solution in the future is what it is right now, plus something. Before, this was delta t times something. Now we have this thing here, and we have to figure out how to deal with this. Now this is where the approximation is going to come. Part of the reason you can't evaluate this is because you want to know the solution y from right now into the future. Well, you have it right now, and when you evaluate this, it's evaluated from t of n to t of n plus 1. It's evaluating the future. Well, you don't know what y is in the future. That's the whole point. So you have to figure out a way to approximate this, because you can't evaluate it otherwise. Okay? So how do we evaluate that? What we're going to do this approximation is to say that f, okay, you guys can't see that, huh? How far down can you see? Is that okay? Yeah? That thing is, what? All right. The idea then is to approximate by saying this f is some polynomial. Okay? So this is where the approximation is going to come. So let's make a simple polynomial. Let's approximate f by the following polynomial. It's a first-degree polynomial, which is some constant. What constant do we want it to be? Well, we'd like to pick something reasonable. How about what the solution is at the current time? Because I know what that is. So let's just pick this polynomial f, which is supposed to be representing f of ty. Let's just pick it to be this constant and the value at the point I actually have. That's a very reasonable thing to do. Now notice what happens when we do that. This is constant. I already know this. So if I put a constant into an integral, it comes out. Right? And what's left there is just 1 times dt. Well, if you integrate dt, you get t. You evaluate it at the 2 endpoints. This becomes delta t. So if I put that in, all I get out from this formula is that constant times delta t. Lo and behold, I have the Euler formula again. Same as before. Okay? So we derive the Euler formula, slightly different method, same result. And now here's where it gets more interesting, which is to say, okay, well, let's get a little bit fancier. Remember, all I know is now and the past. The future's open. So you have to only use now and the past. You can actually use future points. I'll show you that in a minute. But then it becomes a little trickier. Okay. So let's do another approximation. We'll try the following. Approximate f by this polynomial. This polynomial is going to be a polynomial that goes through the current point and 1 point back in the future. So it goes through the current point and the past point. This is a line formula that goes through the current point, t of n, and the past point, t of n minus 1. All you have to do is plug in these two values. So for instance, if you put t of n in here, what do you get? T of n minus 1, this goes to 0. Oh, this is where I do have a typo. Yeah, okay. So so if you go to, anyway, I can't remember how the n's go, if it's n minus 1, I think. I think that's right, like that. In my updated notes, that's there. This is from the old notes, which I should have copied the new notes. All right. So if you put in t of n, this becomes delta t over delta t. They cancel, and you have f of n minus 1 minus f of n minus 1. You're just left with f of n. Indeed, goes to that point. And if you put in t of n minus 1, that goes to 0, and you're just left with f of n minus 1. Okay, there we go. This thing here goes to, so for instance, if I'm trying to predict the value at the point in the future, t of n plus 1, over here, then I need this point and 1 from the past. So I'm using it something that goes to the current point, a past point, to try to get me an approximation for the next point over. Okay, so that's my polynomial. And this goes to these 2 points. So now that I have this, I can take this thing here, plug it in to my integral formula here, integrate. It's a very simple integration. And when you do all that, you end up with the following. Future point is equal to the current point plus delta t over 2. 3 times the current point, f evaluated at the current point, and minus 1, this evaluated at the past point. So this thing here is a multi-step scheme. You need 2 initial conditions, as it were, to generate your next iteration. Okay? So you have the current point, use a past point, and the current point to generate the next point. Then you can use this point plus the next point. It's like you're always playing with 3 time slots, as it were. Okay? That's how you do this. This is called Adams Bashforth. Okay? So Adams Bashforth uses current points and past points to generate future points. And the idea is this is going to be more accurate. Again, we'll talk about accuracy next time. Okay? So this is a different scheme. So you can start seeing the variety of schemes you can come up with in doing this. All right? And people do a lot of PhD projects on such things as these. Okay? So that is Adams Bashforth. Use current and past points to generate some of these schemes, and often get some nice stability properties. But there's no reason why you couldn't use future points. So let's go back and follow what we just did here, and this is called Adams-Moulton. I just love name dropping. Oh yeah, I know this guy. I hung out with him at a party once. Moulton's a cool guy. Adams. Okay. Just joking. I didn't hang out with him really. Okay. Adams-Moulton. Oh, Adams-Moulton says, let's not use just current and past. We'll use also the future and see what happens with that. So instead of this f being, again, we'll approximate by constant. First order polynomial. But now, instead of our constant being the current point, how about it's the future point? Now, this creates certain problems, because now you can do this. You can put in that formula, integrate it. It's a constant again. And what do you get? Y of n plus 1 is equal to y of n plus delta t. F of t of n plus 1, y of n plus 1. Here's your scheme. Now, the problem with this is it's not so easy as an iteration. Why? Because you can't. Here's the future. There's the future. This is a nonlinear system of equations right now. You're trying to solve for y of n plus 1, which is there and there. Okay? So you need a nonlinear solve here. Which begs the question, why would anyone ever do such a thing? Because iteration is easy. When you're having solved nonlinear systems of equations, that costs you a lot of time. Your computer will bog down on that. But the win here is that sometimes this method here, these methods are called implicit methods. Okay? And the implicit methods, what they do is they generate the system where you do have to solve these things. But typically what happens, these have incredible stability properties. Often they do. So like you can take big time steps, you still get good accuracy. Your scheme is stable. We're going to talk about stability of schemes as we go. But that's why people sometimes use implicit schemes. Is because even though you have to pay a price for solving this, which is typically very costly, the stability of your scheme is such that it's worth paying that price. Like I said, for any given problem you have, one of the fundamental evaluations you have to make is how fast do I want it to run, how accurate do I want it to be. Obviously, you have to have a stable scheme. That's going to almost go without saying. But you're always trying to do the trade-off. How much am I willing to risk in my accuracy to get this computation done? Or likewise, how accurate do I need it to be to make the kind of predictions I need to make? And then what's the price going to be associated with that? All right, so that's what Adams-Moulton will do to you, is it will make you solve something like this. Let's go one level up from this, which is a second order Adams-Moulton, which is now if we say f is polynomial degree 2 again. Now what we can do is we're going to use, again, let me see here. Do I have it? Yeah, I think this is it here. Yeah. So now I'm going to do a line which goes through the current point and the future point. This is a lot like, this is now a second order polynomial to approximate my solution. It goes through the current point, the future point, and what I'm going to do is take this thing here, put it into my formula over there where I'm using a polynomial in place of f, integrate it. Very simple to do. And what I end up with is the Adams-Moulton scheme, which looks something like this. Hold on 1 second here. Oh. Okay, t of n plus 1. Y of n plus 1 plus f of tn yn. Solution in the future is what it was in the past, delta t over 2. F evaluated in the future plus f evaluated now. And again, this is the hard part. You don't know what f is in the future. So this makes you solve a nonlinear system of equations. Okay, here is a really cool idea. One of the reasons you want to use methods such as this that are implicit is because they have great stability properties. Great. Huge price tag to pay for it, though. Solve this nonlinear system of equations to get this nice stability. One of the beauties of straightforward iteration is that you just put this in and let it go. Cycle through. This thing will rip through things. You don't have to solve anything. There's no overhead here. You just have this three-stage process. Your 2 points give you the next one. The 2 points give you the next one. Nothing to think about. Not as good stability properties. Is there any way to put these two together? Indeed, there is. Thus, I would ask the question, because otherwise I would just not ask the question, right? So when I ask the question, you know there's a good answer. Although maybe I should just ask questions that there's not a good answer to, and then nobody would really know. So here's what happens if you do that. It's called predictor-corrector methods. So again, I don't know if some of you have heard these terms before, but if you have, this is the essence of the idea. So let's come back over. I'm going to do a little fancy camera work here in a minute. This is nice because it's just straightforward. Gives you a future point at very little cost. This is nice because it has nice stability, but you have to have that future point. So predictor-corrector says is, well, why don't we still try to use some of this implicit nature of this? And instead of using the future point, why don't we use an approximation to the future point? In particular, I will approximate the future point with this one. Right there. I will say, my future point, this is my prediction for what the future is going to look like, is this. Comes right from that Adams Bashforth scheme. I'm predicting that's what the future is. Now, from that, I'm going to put that predictor step into my Adams Moulton. So my solution now is going to be y of n plus delta t over 2. This thing evaluated f at t of n plus 1, y, my predicted value in the future, minus or plus f. So instead of solving a system of equations, what I've done, I've overcome by saying, this was the problem before because I had a y of n plus 1 in there, which I did not know. But now what I can say is, why don't I use the predicted value I got? So I'm kind of using the implicit scheme, but not really. These predictor-corrector methods tend to have very good stability properties. Okay? And that's why you would tend to use them. So these are some of the ideas and outlines of some of the standard stepping schemes you will come across. There's multiple step. There's Runge-Kutta. Runge-Kutta is probably one of the most famous. Implicit versus explicit. You'll see implicit being used on problems where there are some issues about the problem itself, about where you need the stability properties. And often if you need really good stability, people will go to implicit, even though it costs you to do it. Sometimes that's the only way you can get reasonable results. And then you have these hybrid methods, which are sort of a combination of multiple stepping, predictor, and also using implicit, explicit ideas together to actually get you something fairly accurate. Okay, I think that's pretty much it for our time. Wednesday, we will have, we'll talk about the error analysis of this. And the other only thing I have is I have a list here of everybody's names that's signed up for the course with emails. I'm going to put you on an email list. If you have an email that's maybe different than this, if you don't mind just kind of taking a look at this, if you want it sent somewhere differently, please cross off what's here and write where you want me to send it, because I will send an email out probably tomorrow with the web page address and any other information you need to know, also where the notes can be found, so you can have all that. So please check that. Enjoy your first day.